Let us discuss about inequalities and their solution sets. Say for example, we have an ordinary equation 3x minus 4 equals 0. The value of x that will satisfy this equation is x equal to 4/3. So we say that the solution set for this equation will contain the number 4/3. There is no other number that will satisfy the equation 3x minus 4 equal to 0 except other than 4/3. No? If you have an equation x squared minus 4 equal to 0, the possible values for x here are -2 and +2. So we say that the solution set for the given equation will contain the numbers -2 and 2. For x squared plus 1 equal to 0, if x is a real number, there will be no real solution for x squared plus 1 equal to 0. So we say that the solution set for this equation will be the null set. In each of these three cases, now, the third one has no solution. For the first two, notice that there are finite number of solutions to our equation. Can we say the same thing if it involves inequalities? Say for example, 2x minus 7 is less than 5. Right? So that is the given inequality. We want to find values of x that will satisfy. Say for example, x is 10. Say x is 10. 2 times 10 is 20 minus 7 is 13, and that is not less than 5. So that is not a solution. So, that is not a solution. How about when x is 1? 2 times 1 minus 7 is that less than 5. -5 is less than 5. That is true. So x equal to 1 is a solution. How about x equal to 0? 2 times 0 minus 7, is that less than 5? -7 is less than 5. Yes. So x equal to 0 is also a solution. How about x equal to -3? X equal to -3. That will be 2 times -3 minus 7, is that less than 5? -6 and -7 is -13, and that is indeed less than 5. So again, x equal to -3 is a solution. We can go on and on and on. No? The solutions are not limited to whole numbers or integers. No? You can also say -0.1. No? So that will be -7.2, which is less than 5, if your x is -0.1. So you can go on, and you cannot possibly enumerate all these solutions. So at this point, you should have realized that the solution set is infinite. There are infinitely many solutions to the given inequality, 2x minus 7 less than 5. So that's what we're going to do. We will look for the solution set, or the set of numbers satisfying a given inequality. So we work on the following numbers. Alright, so we find the solution set of the following inequalities. So let's start with 3x minus 5 greater than 2x plus 1. Similar to ordinary equations, no, we combine all terms containing the x variable and all the pure constants to the left. And how do we do that? No? For 3x minus 5 greater than 2x plus 1, we have to get rid of 2x at the right side. So we have to add -2x to both sides. Or in other words, we just have to transpose 2x to the left. So it becomes 3x minus 2x. No, we are actually adding negative 2x to both sides. Yeah? And negative 2x times 2x will vanish. All right? And we are allowed to do that. No? One of the theorems says that adding a constant to both sides of the inequality will not change the inequality. If it is greater than, it will remain as greater than. No? Whether we add a positive number or a negative number. So it remains greater than. And the negative 5 to the other side, we add 5 to both sides. 5 and negative 5 is 0. 5 and 1, that will be 6. And let us just write 5 plus 1. So 3x minus 2x is x, greater than 5 plus 1 is 6. So x is greater than 6. No? And this is equivalent to the interval x greater than 6, 6 to positive infinity. Since it is a strict inequality, it must be open at 6, open at positive infinity. So we shall write the solution set as the interval, containing the interval 6 to positive infinity. Any number in this interval will satisfy the given inequality. Right? So 6, 6.1, 6, of course, the endpoint, it is not included. So 6.1, 6.01, 5, not 5, 8, 10, any number greater than 6 will satisfy the inequality. All right? We go to the next one. Say x over x minus 1 is less than 2. So, we have to get rid of x minus 1. What we normally do is we multiply both sides. No? Multiply both sides by x minus 1. No? We cross multiply. Cross multiplying will be getting x 2 times x minus 1. But remember, we have a theorem that says that if A is less than B and C is positive, AC is less than BC. But if C is less than 0 or negative, this one will become AC greater than BC. So we have to consider two cases. In our problem, we are multiplying both sides by x minus 1, and we do not know whether x minus 1 is positive or negative, because we do not know the value of x. We do not know the value of x. If we only know the value of x, we'll be able to find the sign of x minus 1, right? And if we know the sign of x minus 1, we would know if we will retain the inequality less than or reverse the inequality. So we have to consider both cases. For case 1, x minus 1 is greater than 0. So meaning to say that it is positive. That is equivalent to x greater than 1. X minus 1 is greater than 0. That means that x is greater than 1. So that is the constraint. That is the constraint for case 1. We're considering all numbers greater than 1. And then, what will happen to our inequality? Multiplying both sides by x minus 1, we'll be getting x and 2 times the quantity x minus 1. And is there a need of changing the inequality less than to greater than, or we retain the inequality? We retain. No? It remains as less than. Why? Because the multiplier is positive. Okay, so let us now work on this. X is less than, we distribute the 2, 2x minus 2. We transpose 2x to the left, so x minus 2x will give us negative x, less than negative 2. Now, how do I get rid of negative 1? We have negative x. I want it to become positive x. So I'm going to multiply both sides by negative 1. Okay? But multiplying by negative 1, we need to change the inequality. So multiplying both sides by negative 1, we'll be getting x and positive 2, but the inequality less than needs to be changed to greater than. Alright? We need to reverse the inequality from less than to greater than because we are multiplying both sides by a negative number. Okay, so it results to the inequality x greater than 2. That happens when x is greater than 1. So we need to find the intersection of these two. We started with x minus 1 greater than 0, or equivalently x is greater than 1. And we ended up with the inequality x greater than 2. So let us indicate in the number line those numbers, 1 and 2. The first inequality says that x is greater than 1. There. So from 1 to positive infinity. The second inequality says that x is greater than 2. X is greater than 2. There. Where is the intersection? No? Where is the intersection? It will be the set of numbers greater than 1 and at the same time greater than 2. So it should be this set of numbers. Alright? So the solution set, no? For case 1 alone, for case 1 will be from 2 to positive infinity. And since it is open at 2, we use an open parenthesis to positive infinity. Okay? That is for case 1, when x minus 1 is greater than 0 or when x is greater than 1. So we now proceed to the second case, that is when x minus 1 is less than 0. So we proceed to case 2, where x minus 1 is less than 0. And if it is less than 0, that means that it is negative. Okay? That is equivalent to x less than 1. Let us encircle that. So we're considering now x's that are less than 1. And see what will happen when we multiply both sides by x minus 1. We will still be getting x and 2 times x minus 1. But because we are multiplying by a negative number, in here, we are multiplying both sides by x minus 1, which is a negative number, we need to reverse the inequality. From less than, it should become greater than. Alright? So that should be greater than. Then we work on this inequality. So x is greater than 2x minus 2. Once again, we transpose 2x to the left. That will be negative 2x and x, or negative x greater than negative 2. And multiplying both sides by negative 1 to make negative x positive, that becomes x less than positive 2. Okay? So negative x is greater than negative 2. We multiply both sides by negative 1. And being negative, greater than becomes less than. And x is less than 2. So that is the other inequality. We generated the inequality x less than 2 starting from x less than 1. So let us find the solution set for case 2. We indicate the numbers 1 and 2. X is less than 1. So it should be the numbers left of 1. X less than 2, it should be all numbers less than 2. And where is the intersection? The intersection will be the set of all numbers from negative infinity up to 1. So we write the solution set of case 2 as the interval negative infinity to 1. So we have the solution set for case 1 and the solution set for case 2. We write down the solution set for the given inequality. So the solution set will be the intervals. Let me start with the negative ones. Negative infinity to 1 together with the interval 2 to positive infinity. Okay? Or you can just write this as negative infinity to 1 union 2 to positive infinity. Okay? So all numbers from negative infinity to 1 and the set of all numbers from 2 to positive infinity. Okay. Let me show you an alternate solution without indicating or specifying the cases. So the alternate solution will be shorter and easier to do. Okay, so what we do is we transpose 2 to the other side. So this will be the alternate solution. X over x minus 1 minus 2 is less than 0. And then we combine the two fractions here. No? Actually, 2 is also a fraction 2 over 1. So we combine the two. We have the least common denominator x minus 1, x minus 2 times x minus 1 less than 0. Now, combining x over x minus 1 and negative 2. Now, the numerator becomes x minus 2x plus 2, or simply negative x, no? X minus 2x plus 2 over x minus 1 less than 0. Then we are going to get the critical numbers by just equating all the factors to 0. Negative x plus 2 is 0, x minus 1 is 0. Okay? So what are the critical numbers here? X is equal to 2. Negative x plus 2 is 0, or x equal to 2. The other one, x minus 1 is 0, or x equal to 1. So we have the critical numbers, 1 and 2. Let us indicate in the number line the numbers 1 and 2. From these critical numbers, we will define the intervals, the subintervals involving the critical numbers 1 and 2. So we have the interval negative infinity to 1. So these numbers. Then the interval 1 to 2. The interval 1 to 2. And finally, the interval 2 to positive infinity. 2 to positive infinity. So it will be these numbers. Right? Next, we create a table. We create a table indicating the intervals. So first column will involve the factors. Then the intervals. What are the intervals? Negative infinity to 1, 1 to 2. Let me just write it as 2. And 2 to positive infinity. Okay? We indicate the factors. What are the factors? We go back to this one. Right? So the factors are negative x plus 2. Negative x plus 2. What else? X minus 1. And then the quotient x plus 2 over x minus 1. And then we write here the decision. Now, whether the interval is in the solution set or not. Right? There. So that's a nice table. For each interval, we get a representative value. No? So from negative infinity to 1, you can use any value, any number in the interval negative infinity to 1. Say 0. 0. So use x equal to 0. And then we indicate the sign in the table. What we are going to input in the table is simply the sign. What will be the sign of the factor if we replace 0 to x? As negative 0 or 0 plus 2, that will be positive. That is positive. How about x minus 1? When you replace x by 0, 0 minus 1 is negative. Then negative x plus 2 is positive over x minus 1, which is negative. Positive over negative, as we all know, is negative. Okay, we go back to our inequality here. This inequality. Okay. Negative x plus 2 over x minus 1 when x is 0 is negative. There, negative. Is it true that it is less than 0? Okay. Is negative number less than 0? Yes. So if it is yes, then that means that the solution set contains the interval negative infinity to 1. Okay, so let's just put a check mark. So that indicates that the interval negative infinity to 1 is in the solution set. We now go to the next interval 1, 2. For 1, 2, let us get a value, say x equal to 1.5, and see what will be the sign of the factor. So if x is 1.5, negative 1.5 plus 2 is positive. 1.5 minus 1 is positive. Positive over positive is positive. Negative x plus 2 is positive. And x minus 1 is also positive. So if you take the quotient, it will also be positive. But is a positive number less than 0? Is a positive number less than 0? No. So let us put an x there to indicate that the interval 1, 2 is not in the solution set. Finally, we go to the interval 2 to positive infinity. Let us say that x here is equal to 3. So let us see what will be the sign of the factors. So negative 3 plus 2 is positive. Oh, I think it is negative. No? Negative 3 plus 2. That should be negative. Negative 3 plus 2 is negative. Then 3 minus 1 is positive. Negative x plus 2 is negative divided by x minus 1, which is positive. The answer is negative. And we know that a negative number is, again, less than 0. So we put a check mark there. So we're done. Now we just have to write the solution set by collecting all the intervals. Now where the representative values satisfy the inequality. So the solution set here will be the intervals negative infinity to 1 together with 2 to positive infinity. Or we can just write it as negative infinity to 1 union 2 to positive infinity. Okay? And this agrees with our previous answer. Okay? This agrees with our previous answer. Let us have another one. Let us work on 3x squared minus 14x plus 15 less than 0. Let us say less than or equal to 0. Okay, so what do we see here at the left side of the inequality? Quadratic expression And I think it is factorable into, let us see, what are the factors? 3x and x, and then that could be negative 5 and negative 3 less than or equal to 0. So we check. 3x times x is 3x squared. Negative 5 and negative 3 is positive 15. Negative 5x and negative 9x is negative 14x. So we have the correct factors. Now, just like what we have done earlier, we just have to get the critical numbers. So we simply equate 3x minus 5 to 0 and x minus 3 to 0. So x is 5/3 and x equal to 3. We create a number line. We indicate the numbers 5/3 and 3. So 5/3 is 1.67. Then the other one is 3. So what are the intervals? What are the intervals? We write here the factors and then the intervals. The factors are 3x minus 5, x minus 3, and the product is 3x minus 5 times x minus 3. The intervals are negative infinity to 5/3, 5/3 to 3, and 3 to positive infinity. Okay? So this will be for the decision. Alright? Let us indicate the numbers that we're going to use coming from each interval. From negative infinity to 5/3, well, we can use 0. From 5/3 to 3, 1.67 to 3, well, we can choose x equal to 2. 3 to positive infinity, we can use x equal to 4. Okay? We supply the signs. When x is 0, 3 times 0 minus 5 is negative. 0 times negative 3 is 0 minus 3, rather, is negative. So 3x minus 5 is negative, x minus 3 is negative, the product is positive. Is a positive number less than 0? No. Okay? So it's a big no. How about x equal to 2? For x equal to 2, 3 times 2 minus 5, that will be positive. 2 minus 3 is negative. Positive times negative is negative, and negative is less than 0. Right? So, put a check mark. How about x equal to 4? 3 times 4 minus 5 is positive. 4 minus 3 is positive. 3x minus 5 times x minus 3, both positive, so the product is positive. Of course, that is not less than 0. Okay? So we have the interval 5/3 to 3. But notice that it is a non-strict inequality. So what we do is we check the endpoints. No? 5/3. The endpoint 5/3. If x is 5/3, what will happen to 3x minus 5? It will become 0 multiplied by x minus 3. That will still be 0. Is 0 less than or equal to 0? Of course. No? So that means that the endpoint is included. How about the other endpoint 3? When we substitute x equal to 3, x minus 3 will become 0, and multiply to 3x minus 5, that will also be 0, and 0 is less than or equal to 0. So 3 is also in the solution set. So the solution set for the entire inequality will be the interval 5/3 to 3 and close at both ends. Right? As an exercise, find the solution set of the following. The first one is 3 over x plus 3 less than 1 over x. And the other one is x times x minus 2, 2x minus 7 greater than or equal to 0. Okay?